Okay. Good morning. Okay, can you hear me?
Yes, sir.
Okay. Okay. Okay, so I think your friends are still joining. Okay, it's okay. We will start. Okay, so before we start today, okay, okay, before we start today, I just want to give a few announcements. The first is on the lab. Okay, so the lab will be conducted. So based on the polling result yesterday that I gave, so mostly decided to do this week. So the plan will be uh, lab will be conducted tomorrow and Friday. So following the group, and one more group will be next week. Okay, so if any one of you already went back, so you can join on next week lab session. Okay, so if you have any issues with that, so please let me know so that we will try to adjust. Okay, we'll try to adjust. But for tomorrow and also Friday's session, so I'm still waiting for the teaching engineer to confirm to me. Now, because now the degree students already started, so we don't want to clash with a degree students timetable. So okay, so you say will get back to me today. So whatever announcement I will give in the WhatsApp group. Okay, so that's on the lab. Okay, because we only have one more lab to go, and we have 3 weeks. Okay, so now is week number 12, 12, 13, 14. Then you will have 1 week break for revision week before your final exam starts. Okay, so I don't want to cram everything at the last minute. So because we have too many things ongoing, so I think the water issue is the reason one. But I believe all sorted out. Then I think election is also coming soon. I think 19th of November. So I don't know how the university will arrange the timetable. So I don't want to take risk. So I just want to settle all as fast as possible. Okay, so that's the first announcement. The second announcement will be on the quiz. Okay, so we have quiz 2 next week. Okay, quiz 2 next week. We'll be covering chapter 6 until chapter 9, chapter 6 until chapter 8. Okay, maybe chapter 9 also will be included a bit because we already studied about heat transfer in chapter 5. And chapter 5 and chapter 6. So maybe some of the questions will come from there. Okay, so that's another thing. So we still have few more things, assessments to settle. Okay, I already gave lab 2 and lab 4 open-ended in Google Classroom. So please make sure you start doing from now because you need to submit in final week. And because of the election, so maybe you all need to go back earlier. So I don't want you all to have problem later. Okay, so please start to do because I think the experiments are not so difficult. So you can find a lot in internet. So try to do. I think you will spend more time in preparing the lab modules. So if you already finalize the experiment, you can already do by now. So don't wait until last minute. Okay, so that's one thing. Then I have given assignment two. Assignment two, two questions. So I think it came from the lecture note. So if you have, I think even the answers are there. just the final answer. So try to do and submit to electronic access. My electronic access, the quota, the box is there. So please put in the box. Okay, so that I can start marking, and you can uh, get some marks. Because I think assignment 2 is 5 marks of overall. So please don't lose the mark. Okay. So I think that's about it for the announcement. Think nothing much. I think for quiz one, okay, I said I will give uh, another chance for those who didn't take, and those who couldn't score well. So that one I will arrange with you all separately. So when we will do. Okay. Then before the final exam, so we will have an exam clinic. Okay, so we will discuss on what you need to focus for your final exam. So I think after so long, this year we will have final exam face to face after COVID. So it will be not like your open book exam previously. So it will be a bit tough in the sense of you will have lesser reference to go through. Okay, so you need to be prepared. So we will discuss certain things, and we also will have few tutorials for you to get practice with before your final exam. Okay, so before we start, any question? Tadi soalan? Okay, so if no question, so today we will start with chapter 8, part 1. Okay, mass and energy analysis of control volumes. Okay, or we refer as open system. Okay, so we know open system, the volume is controlled, so that's why we call it as a control volume. And in open system, you have mass and also energy. Okay, mass is from whatever materials that you're dealing with. It can be water, it can be steam, so it can be any fluid. And energy is basically on the heat transfer and also the work done. Okay, so for open system, we have three components that will be involved. Okay, so today we will cover part 1, and part 2 we will be covering in at puzzle assignment. Okay, so we start with conservation of energy for control volume. Okay, so conservation of energy uh, for open system or control volume. So you have, as I say, we have mass crossing the system boundary or the control surface. So you can see in this picture, so mass is entering. So at the velocity v1 and leaving the system. Okay, so this mi is mass in. So me is mass exit. So meaning you have a control volume here, volume here, control surface or the boundary. So mass is entering and mass is leaving at the particular velocity. So Q net, so we transfer, and W net is the work done. Okay, so you have a difference in I and all the other parameters. Okay, so basically the mass and energy content of the open system may change when the mass enters. Okay, when new mass is entering in, so the energy inside will change. So that's why we call it as a conservation of energy for control volume, because the energy there will be conservation happening inside. So it as we know, so potential energy can be changed to internet energy. The internet energy can be changing to kinetic energy, and so on. Okay, so thermodynamic processing involving control volume can be considered in two groups. Okay, normally the analysis that we will do, we will have two groups. The first group is steady flow process. A steady flow process meaning over time, so the flow and all the parameters are same. Okay, so it's easier to do when the process is steady flow. An unsteady flow process meaning from point one to point two, within that in to exit. So you have few points with a different, maybe different velocity or different mass entering. Okay, so that's one thing. Okay, during a steady flow process, the fluid flows through the control volume steadily, experiencing no change with time. So if the flow is steady, meaning no change with time. Okay, so that's one thing. Okay, let's review the concept of mass flow rate and energy transport by mass. Okay, one should study the development of the general conservation of mass presented in the text. Okay, so the first thing that you need to understand is mass flow rate. Okay, mass flow through a cross sectional area. So mass flow rate is actually a mass flow through a cross section area over time. Okay, so over time we are taking the integration. Okay, so this is the formula. Okay, so m dot. So normally mass flow rate we will have m dot. We will have the dot. So note that the dot over the mass symbol indicates time rate of change. So when you have dot, meaning so it's related with time. Okay, so um, okay, so you can see in the picture. So this is the actual velocity. How the actual velocity will be? The one nearer to the surface will be almost same. It will be hard to move the molecules, and molecules at the middle it will move more. Okay, so then in the actual situation, the water or the mass will be flowing in this way. But for calculation, we will take average of all this line, and then we will get this. Okay, so it's easier to do calculation. Okay, so this is the formula. Okay, if the fluid density and velocity are constant, okay, over a flow cross sectional area, the mass flow rate is, so you are taking into consideration the average velocity. Okay, not the actual velocity. Okay, so m dot our mass flow rate equals to rho average velocity times with area. Okay, so or you can use this formula or this formula. Okay, so these are the same because this thing is derived from this pipe. Okay, so you can get this. Okay, so density is 1 over V, so you can convert it into this form. Okay, depends on the information given in the question. Later we will see few questions, then you can understand how we can use this. Okay, for your I will give an appendix of formulas. Okay, for your final exam. So some of the formula will be appearing in your uh, exam question at the appendix section. Okay, the fluid volume flowing through a cross section area per unit time is called the volume flow rate. So earlier we see the mass flow rate. So there's another thing that called volume flow rate. So this is actually the fluid volume flowing through a cross sectional area over time. Okay, so the formula is, so the symbol is V dot. A V dot is volume flow rate equals to the average velocity times with area. Okay, and the relation between mass and volume flow rate is this m dot equals to rho V dot, so or equals to V dot over V. V is the velocity. Okay, so you can see one example. Okay, so this is the type of question that can be asked in the exam. Okay, so air at 100 kilopascal, 50 degrees Celsius flows through a pipe with a volume flow rate of 40 meter cube per minute. Okay, so that's a unit for volume flow rate. So find the mass flow rate through the pipe in kg per second. Okay, assume air to be an ideal gas. So when the question is mentioning, you need to find out what fluid is used. Okay, so in this case is air. So air, we assume that it's an ideal gas. So you can use the ideal gas equation PV equals to RT. So you rearrange this, so you will get this. Okay, RT over P. So temperature is given, pressure is given. So R is constant. So for ideal gas, so you can get the value of R from the ideal gas table in your thermodynamic table. Okay, so R equals to 0.287. Okay, so I will show you how to find the R. Okay, so this is your thermodynamic table. Okay, so you have a few table. So just find if it's related to ideal gas. So just find which table is related to ideal gas. So you have few. Okay, normally for ideal gas, we will take from table 2. Table 2. So just go to table A2. The table A1. So go to table A2. Okay, so this is table A2. So earlier we mentioned that it's a air. Okay, so air we assume as ideal gas. And if you want to find the gas constant, so just go and find. So what is the value of R? Okay, so in this table for all the gases, so you have gas constant, the value of R, you have value of Cp, Cv, and also K. Okay, so in this case, we want to find the value of R for air. So the value is 0.287. Okay, so that's how you can find. So if the question mentioned that it's a nitrogen, okay, so you just go and find the value of R, yeah, 0.2968. Okay, normally we won't ask the weird gases. So it can be either air, so it can be either carbon dioxide or helium or hydrogen, okay, or nitrogen or oxygen, okay, or it can be a steam. Okay, steam also can be asked. So steam, the gas constant is 0.4615. Okay, so this is how you can check for the value of R from the thermodynamic table. Okay, so go back to the question. Okay, so we already got the value of R. Okay, so R from the thermodynamic table is 0.287. So T is 50 degrees Celsius. So T will be in Kelvin. So you need to plus 273. And the pressure is in Pascal. So 100,000 Pascal. Okay, so you already got this. So you have a unit conversion. Sorry, no unit conversion. Okay, so once you cancel everything, so you will get the value of V equals to 0.9270 meter cube per kilogram. So that's the first thing. But the question asks you to find the mass flow rate. So mass flow rate you take from this formula, the relation Okay, so M dot equals to V dot over V. So here we know that the max flow rate is 40 meter cube per minute. Okay, and V equals to 0.9270. Okay, so once you solve this, so this is the answer, 0.719 kilogram per second. Okay, so that's for the example. Okay, so conservation of mass for general control volume. So this is for the general. So the conservation of mass principle is sum of the rate of mass flowing into control volume minus sum of rate of mass leaving the control volume equals to and the rate change of mass inside the control volume. So or we can write it like this. Okay, so sum of mass flow rate and in minus sum of mass flow rate out equals to the changes in the mass of the system. Okay, so steady flow process. So meaning the energy conversion device operates steadily over long period of time. So let's say it's a 1 minute, or it can be 1 second or 1 hour. So the flow rate is steady. So meaning it's not changing. So the rate of heat transfer and work crossing this control surface are constant with time. Okay, so it will be easier to calculate when the process is steady flow. Okay, in steady flow, okay, so based on this formula, so no changes in mass. Okay, no changes. So meaning the mass flow rate in minus mass flow rate out equals to 0. Okay, so that's what is mentioned here. So when it's 0, so finally for steady flow of mass, so the equation will become like this, because mass flow rate in minus mass flow rate out equals to 0. So uh, the negative part you bring to this side, so you will get this formula. The sum of rate of mass flowing into the control volume equals to mass leaving the control volume. Okay, and for special case where the fluid is incompressible, okay, the formula will become like this. So m dot equals to rho v dot. Okay, we call it as a constant density. So the density is not changing. Okay, so for one entrance, one axis steady flow uh, control volume, the mass flow rates are related by, so you can see. So there are some cases where there are only one entrance and one exit. So it can be a turbine, it can be a fan. So normally you only will have one entrance and one exit. So you need to evaluate from the question what kind of environment is given. So is it a one exit, one entrance, one exit? So if one entrance and one exit, the mass in and mass out will be the same, because whatever is entering, it will go out. So mass in, the amount of mass in and amount of mass out are the same. So you can have it like this. Then the equation will become rho in v dot in equals to rho out v dot out. Okay, so this is for the incompressible. So in incompressible assumption, density will be the same. So meaning the density in equals to density out. So you replace here. So rho rho in equals to rho out. So the finally we will have um, volume flow rate in equals to volume flow rate out. Okay, so you replace in the formula, you will get like this. So volume flow rate is V in A in equals to V out A out. Okay, so these are the formulas. So word of caution, this result applies only in the incompressible fluid. Okay, so it's most of the thermodynamic system deal with processes involving compressible fluid. Okay, so if the question mentions is an incompressible fluid, then you can use all this formula. But normally the thermodynamic questions will be related to compressible fluid like ideal gas, steam, or refrigerant. Okay, so refrigerant which are not incompressible fluid. All that are compressible fluid. So all this cannot be used. Okay, cannot be used. Okay, so we'll see one example. Okay, so you can see here. Okay, we can see from this image. So this is one entrance and one exit problem. So no exits in between. Okay, so we know from this question is a one entrance, one exit. Okay, so try to read this question. Okay, so the question is so air. So the medium is air. Air enters a nozzle steadily at 2.21 kilogram per meter cube. Okay, and 30 meter per second. A leaf at 0.762 kilogram per meter cube and under 80 meter per second. Okay, so okay, if the inlet area of the nozzle, so the area is given 80 centimeter cube. Okay, centimeter cube. So you need to convert. Make sure you convert it to meter square. So determine the mass flow rate through the nozzle. Okay, through the keyword through the nozzle means so coming out. So exit area. So your inlet area is given. So what is the exit area? So your two things that you need to find. Okay, so assume steady flow, single stream. Okay, so m dot equals to rho 1 v1 a1. So this is from the previous formula. Okay, so rho 1 is 2.21. So v1 is 0.008. Sorry, I need to balik. So v1 is 30 meters per second. So 30 meter per second. And a1 is 0.008 meters square. Because here it is 80 centimeters square. Okay, so you solve this, you will get 0.530 kilogram per second. Okay, so that's for the first part. So the second part, we know that since this is one entrance and one exit, so m1 dot equals to m2 dot. Okay, so you know that the formula is rho 2 v2 a2. So you rearrange the formula to find the area 2 because the question asks to find the exit area of the nozzle. Okay, so you rearrange this formula, you will get a2 equals to m dot over uh, rho 2 v2. Okay, so you replace all the information that you gathered. Okay, so m dot equals to 0.530. Okay, rho 2 is 0.762 from here, and v2 is under 80 meter per second given in the question. So you solve this, you'll get the answer 0.00387 meter square, or if you want to convert it to centimeter square, is 38.7. So you only convert if the question asks you to convert. Okay, sometimes the question will say, so determine exit area of the nozzle in centimeter square. If it's given, then you need to give in that particular unit. So if not, you can just stop until this side. Okay, so this is the sketch. So nozzle. So nozzle will be like this: bigger entrance, a smaller exit. So if you see here, the entrance earlier was 80 centimeters square. Okay, entrance is bigger. So exit is only 38.7, so smaller. Okay, and it will be like this. Okay, so that's for one example we see. Okay, so flow work and energy of a flowing fluid. Okay, so we have seen for the mass flow rate, volume flow rate. Okay, now we want to find the flow work. Okay, and the energy of a flowing fluid. Okay, we know work is related to force times distance. Okay, W equals to Fs. Okay, Fs. So meaning you need to apply a force to move one thing from one point to another point. So that is what we call as work. And in open system, so you can see you have a system here. So you're applying a force and it is moving from this point to this point. Okay, of a length of L. Okay, so we know that there's a work done by the flow because it's moving from one point to another point. Okay, so using that approximation, so you can find that workflow. Okay, energy flow into and from the control volume with the mass. The energy requires to push the mass into or out of the control volume is known as the flow work or flow energy. Uh, so you need to apply a force to move the fluid from one point to another point in the control volume. The fluid upstream of the control surface acts as a piston to push a unit of mass into or out of the system. So this is the upstream. Okay, so upstream is where the force starts. So consider the unit of mass entering the control volume shown below. Okay, so boleh tengok dekat sini. So you have a control volume here. So you're applying a force. So it's like a piston when you apply. So the mass is entering the control volume and going out. Okay, as the fluid upstream pushes mass across the control surface, work done on the unit of mass is, so the work done flow equals to F times L, because work is F times S, or the distance, force times distance. So here the distance is L, so it's FL. So F equals to PA. So PA, so you can have a PAL. So area times length is volume. So it also can be in volume. Okay, so it also can be in this form. So mass times the volume flow rate. Okay, so the in terms of per unit mass, per unit mass, so W jadi kecil, the smaller W. So this is work done flow over M. So here you cancel, so M and M you can cancel. So you'll have pressure times volume flow rate. Okay, so these are some of the formulas that you can use in your calculation. Okay, the term PV is called the flow work done in the unit of mass if we cross the control surface. Okay, so that's on the work. Then we can see about the total energy. Okay, total energy of the flowing fluid. Okay, so total energy carried by unit mass as it crosses the control surface is a sum of internal energy, flow work, kinetic energy, and potential energy. Okay, so I think this is from chapter 6. Okay, chapter 6, we know the total energy of a system is summation of internal energy. Internal energy is U. Flow work is PV, KPV. Kinetic energy, of V square. Okay, so or V square over 2. Potential energy is Gz. Okay, so total energy, let's say, is theta. Okay, so U plus PV, we know that is a H or the enthalpy. This is also from the previous lectures. You can go and see. So U plus PV equals to H. Okay, so you can use this formula or this formula. Okay, so energy transported by mass. So amount of energy transported across the unit mass equals to so energy mass equals to m theta. So theta is from this formula. So here it takes the second formula. So m h plus v square over 2 plus gz. Okay. So all these can be used to calculate. Okay, and we also can have the form in the rate of energy. So rate of energy means per time. Okay, so E dot mass equals to m dot over q, and you apply the same formula. Okay, it depends on what the question asks. So you have a lot of stuff related to open system. If the system asks to find the rate energy, then you can use this formula. If the system asks to find the energy, then you can use this formula. So if the system asks to find the total energy, then use this formula. So depends on what the system asks. But in these slides, we are studying all the things that available related to open system. Okay, then we have a conservation of energy. Okay, so if you want to calculate, so you need to go through the conservation of energy principle in order to find some missing parameter. Okay, the conservation of energy principle for the control volume or open system has the same word definition as the first law for the closed system. So meaning energy rate of energy flowing in or E dot in, so minus E dot out. So sum of rate of energy flowing from the system is the changes in the system. Okay, so considering that the energy flow into and from the control system with the mass. Okay, so we know open system, it won't involve mass. So energy enters because that it is transferred to the control volume, and energy leaves because control volume does network uh, on its surrounding. Open system or control volume, the first law become like this. Okay, so Q net so is added to the network net e transfer is Q dot net plus this is for the mass flowing in minus work done by the system minus mass out equals to the changes of energy in the system. Okay, so this is the formula, previous formula. So E in minus E out equals to the changes of energy. So you can rearrange this. You can substitute. Okay, E in is in the form of mass in and also E transfer, and E out in the form of releasing work and also at the exit. So you can find the changes of energy in the system. Okay, so we will study all the theory part first. Then we will see if we question for you to understand. Okay, so steady flow conservation of energy. So since the energy of the control volume is constant with time during the steady state, the conservation of energy principle become so since the energy is constant, so here the changes of energy become zero. So you will have E in dot equals to E out dot. Okay, so you replace back in this formula, so you can generate this particular formula. So Q in plus W in plus the summation of mass times with Q. So this is Q. Yes, Q in equals to Q out plus W out plus summation of mass exit times with Q out. Okay, so you can summarize. Okay, so you just put this at one side. So you can get this formula. So it's all rearranging of the formula. Okay, from the previous derivations. Okay, so Q net dot equals to Q in dot minus Q out dot. Okay, W net uh, dot equals to W out not dot minus W in dot. So you can use this. Okay, so we will take 5, then we will continue. Okay, so now is 8:43. We will continue at 8:48. We will study few more things related to this. Okay, we will continue. Okay, so a number of thermodynamic devices such as pump, fans, and compressor, turbine, nozzles, diffuser, and heater operate with one entrance and one exit. Okay, so contoh, okay, water heater. Okay, so it's only having one entrance and also one exit. So similar. Okay, the steady flow conservation of mass and first law of thermodynamics for this system reduced to, so the mass entering. So when one entrance and one exit, so the mass will be the same. Okay, so m1 dot, so this mass flow rate, m1 dot equals to m2 dot. Okay, so m1 equals to uh, r1 over v1, okay, v1 a1. Okay, or normally we will write that, so v1 a1 over v1 equals to 1 over v2, okay, v2 a2. Okay, so this is the uh, formula, and this is from the previous formula, this formula. So you rearrange, you will get like this. So h2 minus h1 plus v22 at v2 square minus v1 square over 2 plus g uh, z2 minus z1. Okay, where the entrance of the control volume is state 1. Okay, so and in is 1. Okay, whatever 1 is from the inlet, and exit is normally will be 2. Okay, so when we can neglect the kinetic and potential energy terms in the first law, consider the kinetic and potential energy per unit mass. Okay, so we will know. Okay, so this is an example. So for V equals to 45, so kinetic energy is 45 over 2. Okay, so these are just some numbers. These are numbers when you replace it. Okay, for different values of V's and Z's. Okay, so you can see the values are changing. Okay, so when compared to the enthalpy of steam and the enthalpy of air, the kinetic and potential energy are often neglected. Normally what they are saying, for steady flow for one entrance and one exit, so normally we will neglect the kinetic and also potential energy. Okay, so when we neglect the kinetic and potential energy from this formula, so kinetic energy is this and potential energy is this. So when we neglect, we make it 0. So finally we have q dot minus w dot equals to m. So only the value of enthalpy are there. So that's why you only get this formula, because the kinetic and potential energy becomes 0. Okay, from the previous formula. And per unit mass, you can write it like this. Okay, so write it like this. Okay, so these are some of the derivation that you can use. Okay, some steady flow engineering device. Okay, so you can see nozzle will be like this. Okay, nozzle normally you will see at a petrol station. Like, we always say nozzle. Kita selalu sebut nozzle. So letak nozzle. So nozzle, it will be like this because the oil tank, the petrol tank will be big, and at the outlet, okay, to your car, so it will be smaller. So nozzle will be like this. Then the opposite of nozzle is diffuser. So diffuser will have a smaller entrance and bigger exit. Then we have a throttling device. Throttling meaning increasing in speed. Okay, increasing in speed. So your throttle can be increasing in speed, or we also can say that it's a restrictor. Okay, you control the flow. Okay, like pipe. Okay, the pili. Okay, so you have the water tap, so you can control the flow. Okay, then you have a turbine. This is a turbine, so you have a mass in and mass out, and uh, it will enter. So you need to understand that when the space or the area is small, the pressure will be high. When the area is big or the volume is big, the pressure will be low. So in turbine, when it enters, pressure will be high, and when it leaves, the pressure will be low. Okay, and compressor will be opposite. Compressor, when the pressure is entering, the pressure will be low, and when it leaves, the pressure will be high. Uh, and we have a mixing chamber. So you have two fluids you are mix here, and it goes out together. Okay, so you have a mixing chamber, and you have a heat exchanger. So heat exchanger, normally you have a fluid moving through the path into the system. Then you have coolant entering and leaving at the back. So selalunya ada macam ni lah. So let's say this is steam, okay, ataupun wap air. So it's entering and it's going through this pipe. And dekat sini you ada coolant. Okay, katakan ais batu. So ais batu you letak dekat sini. So what will happen? The steam will pass by and the heat will be transferred to the coolant. Okay, so heat from the steam will be transferred to the coolant. So the steam inside will become cool down. Okay, so the temperature will drop. So this is a function of heat exchanger. Okay, most of this system we will study in the next semester. Okay, in pneumatic and hydraulic, you can see how the compressor work, how the throttling valve work, okay, how the mixing chamber works, how the heat exchanger work. So whatever we study in thermodynamics will be applied in pneumatic and hydraulic next semester. Okay, so you will understand better that time. Okay, so you'll see a few things about nozzle and diffuser. So nozzle we saw earlier. So nozzle normally will be like this. Okay. Okay, so for first thing you need to understand, you see the area of the entrance and the exit. Okay, so kita tengok permukaan ataupun keluasan entrance dengan exit. Okay, so kalau keluasan besar, if the area is big, the pressure will be lesser. If the area is small, the pressure will be more. Okay, so this nozzle and this is diffuser. Setup dia berlainan, so the setup is different. Okay, for flow through nozzles, the heat transfer, work, and potential energy are normally neglected. Okay, so we will use the same formula for everything, but we will neglect certain things. Okay, so macam dekat sini, so heat transfer is neglected. So meaning Q net is neglected. Q net kosong, 0. So work is neglected. W is 0. Potential energy are neglected. Because the system is like that. It's a moving system. So no potential energy. So potential energy is neglected. So GZ is neglected for both sides. Okay, so what left? So you only have mass, H, and also the kinetic energy side. So that's why you only have this. Okay, for nozzle and diffuser. Okay, so M H1 plus V1 square over 2 equals to M H2 plus V2 over V2 square over 2. Okay, so if you want to find one component, then you can rearrange this formula in order to find. Okay, so we'll see one example. So you can see this example. Okay, so in this example, I hope you already read. Okay, steam. Okay, so we are using steam. Okay, steam is still falling under the ideal gas. So if you see the table earlier, table A2, so the last line is steam. Okay, steam 0.4 uh, 0.4 million pascal. So it's enters a nozzle. So meaning this is P1. So temperature one T1 is 300 degrees Celsius. So diabetic. So meaning no energy transfers. Okay, with a low velocity. Okay, so velocity is not given. And least with 0.2 million pascal. Okay, 0.2 million pascal is P2. Okay, quality is X. So if you still remember chapter 6, so quality is normally we will give in the value between 0 to 1. So if 90% meaning 0.9 is 0.9. Okay, so you need to understand. So find the exit velocity. The exit velocity is V2, okay, in meter per second. So you do some analysis. So it's a control volume because it's a nozzle. So it's already mentioned here. So property relation. So you can find in the ideal gas about ideal gas in table A2. But if you want to relate it with uh, the temperature and also the pressure, so you need to see the steam table. The steam table I will show you later. So assume the process is air diabatic, which is mentioned here, and it's a steady flow. A steady flow over time is not really changing. And so it is one entrance and one exit. So you can add it here. Okay, conservation principle. First, you start with conservation of mass. For one entrance, one exit, the conservation of mass may come. So the mass flow entering and mass flow out is the same. Okay, so M1 dot equals to M2 dot equals to M. So you can just write it as M dot. Okay, then we go to conservation of energy. So normally we will do both of this. First, we do conservation of mass, then you do conservation of energy. Don't mix it. Okay, so for the analysis. So according to the sketch control volume, the mass crosses the control surface, but no work or heat transfer across the control surface. So you neglect. Because we know from this formula, for nozzle, you straight away take this formula. That's why you're getting this formula here. So energy in equals to energy out. So this is the formula. Okay, so neglecting the inlet kinetic energy. So kinetic energy, so you neglect because it is saying a low velocity. Okay, so the remaining will you only have this. So this is coming from this formula. It is formula. So you neglect this. So you only have square root of 2 h1 minus h2. You are doing this. So you need to find the value of h1 and h2. Okay. How to find? So you need to refer to the thermodynamic table. Okay. So here you have. Okay. So first we find. Okay. How to find? You need to find the enthalpies from the steam tables. So we have few steam tables. Okay, so how to find? So see the temperature. So temperature is 300 degrees Celsius. So if 300 degrees Celsius, this is superheated. Okay, because even 100 degrees Celsius already heated. So if 300 degrees Celsius is superheated, so we try to find in the superheated steam table. Okay, so I will show you how to find. So 300 degrees Celsius. I will show you. So we go to the steam table. Okay, if it's related, I will give in the exam question appendix. Okay, so you can see this table. Okay, first you go to the first uh, table of contents. So you find for superheated steam table. So where is it? So this is saturated water, superheated water. Okay, so table A6. So if other materials or superheated refrigerant, so if the question say 134 refrigerant, then you can revert to here. So for now, we are looking at this table A6. So go to table A6. Okay, so this is table A6. So you have quite long. Okay, so table A6 starts here. Then from the question earlier, so it says the temperature T1 is 300 degrees Celsius and pressure is 0.4 million pascal. So first you find, because the table is arranged based on the pressure, so 0.4 million pascal, so you go find for 0.4. So P equals to, okay, so 0.4 is here. Okay, so pressure is 0.4. Then you find for the temperature 300. So 300 is here, so you will take these values. Okay, what you want to find? So you want to find the value of each. So you just take the value of each from here. So for 300 0.4 million pascal, the H is 3067.1. Okay, so you already found 3067.1. Okay, so I show you back the question. Okay, the question. Okay, so 300. So for 300 superheated, 300 degrees Celsius and 0.4 million pascal. So H1 we already found from the steam table, superheated steam table. So H1 equals to 3067.1 kilojoule per kg. So that's for the first part. Okay, so we already found for the first part. Now we find for the second part. So this is a saturated mix. Okay, so the pressure is 0.2 million pascal and the the value of x2 equals to 0.9. Uh, the quality is 0.9. Okay, so how to find the quality? So quality is, so you can refer to this chart. So this is temperature versus the volume chart. So you have, this is the curve. So you have few points. So this area is liquid and also gas. So the your water is passing through few stages, okay, from 0 to 400. So if 0 to 400, so you know that, so this is starting from the liquid state to the vapor state. Okay, so in between, so you know it's a saturated liquid. So you have a critical point here, then you have a saturated vapor. Okay, and these regions are called a superheated region, meaning is temperature and also the pressure is very high. Okay, so if you want to find the quality X is V minus VF over VFG. So VF and VFG we can get from the steam table. Okay, the value. Okay, you can get from the steam table. And this question, so we know that the value of x is given. X is 0.9 is given. So you just need to find, okay, we can find the value of V. We can find uh, VF and VFG we can get from the steam table. Okay, so we can use this formula to find. Okay, so we go back to the truth table and the steam table, sorry, and the thermodynamic table. So this is a saturated mix because the quality is not fully superheated. It's a more saturated vapor. It's in the saturated vapor condition. If the x value is 1, then we consider it uh, as superheated. Okay, so we try to find. Okay, at 0.2 million Pascal, we try to find the value of HF and also HFG. Okay, so we go back to the thermodynamic table. So I will show first. Okay. So which table to take? Okay, so you have because it's in the saturated condition, so we can either take related to temperature table, saturated water related to temperature table, or saturated with pressure. Because earlier in the question, the pressure is given, so we use A5. Okay, go to table A5. Okay, so this is A5. So you can see in this part, so all the specific volume, internal energy, enthalpy, entropy, all are given. So our concern is from the question, we want to find the value of each. So we just concern on this. Okay, so refer to the question. The question say P2 is 0.2 million Pascal. 0.2 million Pascal is 200 kilopascal. Okay, so this is the values. Okay, first we want to find the value of HF. Okay, for 200 kilopascal or 0.2 million Pascal. So the value of HF is 504.7 and value of HFG is 2201.6. Okay, so these are the two values that we need for the equation to calculate the value of each two. Okay, so 504.71 and 2201.6. Okay, so we already got the values. Okay, so we go back to the question. That's the question. Okay. Mm, okay, so this question is mentioning that for P2 0.2 million Pascal, the H2 is calculated from this at 0.2 million Pascal. HF we already got earlier 504.7 and HFG equals to 2201.6 kilojoules. So this is from the table, saturated water table. Okay, so you already get. Okay, now we want to calculate H2. So H2 is HF plus X2 HFG. So HF we know from the table, HFG also we know, X2 is given in the question. So this is one formula that will be used to calculate from the table. Okay, it's from the table. Okay, so you just replace with the values 504.7 plus 0.9 times 2201.6. So you get H value of H2 equals to 2486.1 kilojoule per kg. Okay, so that's for the first part. Uh, then the question asks to find the exit velocity in MOS. So exit velocity is V2. V2 is, so you use this formula. Okay, use this formula. So you already know the value of H1 and H2. So it's easier to find V2. Okay, so 2 3067.1. So this is from this part minus 2486.1. So it's from here. So unit conversion. So the value of V2 is 1078 millisecond. Sorry, meter per second. Okay, so this is how you answer the questions related to this part. Okay, we'll see one more example. Okay, so the question saying that this is a refrigerant 134A. A refrigerant 134, normally we will use in air condition or in the fridge. Okay, so depends. Okay, so read the question first. Okay, so refrigerant 134A at 700 kPa and 100 degrees Celsius enters. So here the property relation is superheated refrigerant. So because it's 100 degrees Celsius, superheated. Uh, so it's a diabetic nozzle. So it's a nozzle control volume. So steady flow. So it's a diabetic. So velocity. So the first part, pressure 1, P1 equals to 700 kilopascal. So T1 is 100 degrees Celsius because it enters. Uh, velocity is 20 millisecond and leaves at 300. So P2 is 300 kilopascal and temperature T2 is 30 degrees Celsius. So determine A, the exit velocity, and B, the ratio of inlet to exit area. So exit velocity is V2. V2 and ratio of inlet to exit area. So A1 over A2 because ratio. So bagi. Okay, so division. Okay, so we already know all this information. Yeah, normally I will encourage for you to draw the sketch. Okay, so it will be easier for you to see and understand. Okay, we start with conservation of mass. So always start with conservation of mass. Okay, for one entrance and one exit, the conservation of mass become, so M1 equals to M2. So we only consider it as M because they are the same. So then we go to conservation of energy. Okay, according to the sketch control volume, the mass crosses the control surface, but no work or heat transfer crosses the control surface. Neglect the potential energy. So we know for nozzle, We automatically follow because it's nozzle. We will just take this formula. Okay, so we take this formula. Okay, you rearrange the formula. So you just bring everything to one side. Then M and M you can cancel. Then you have uh, okay, so you can rearrange. So bring all this to this side, so you can get the formula in this form. So 0 equals to H2 minus H1 plus V2 square minus V1 square over 2. Okay, so you already got this. Now you want to find the value of um, H2 and H1. So you need to see from the property table. Yes, as mentioned here, the table A13. Okay, so we will try to check. Okay, sorry that I need to shift few times. Okay, okay, table A13. So as you can see here, so table A13 is superheated refrigerant 134. Yay. So you straight away you can know from the type of um, substance and also the process. So process is repeated. So we know that we need to refer to table A13. So just go to table A13. Okay, so this is table A13. Okay, so refer back to the information given. The information given is P1 equals to 700 kilopascal and T1 equals to 100 degrees Celsius. 700 kilopascal is 0.7 because this is in million pascal. So just go to 0.7. Okay, so 0.7 is here. Okay, 0.7 and the temperature is 100. This 100 and 0.7. So all these parameters can be involved. So what you want to find? You want to find the enthalpy. So enthalpy is H. H is 338.04. So you want to find um, V1 also. Okay, the volume. Okay, so the you can get two information here. H is 338.4 and V equals to 0.040642. So two things that you can take. Okay, then for the second part, P2 is 300 kilopascal. So 300 kilopascal meaning 0.3 because it's million. So go to 0.3. So here you can see in this chart, because thermodynamic table, we have a few versions. Okay, so it depends on the company. So in this thermodynamic table that I got from internet, so it only giving 0.28 and 0.32. But the question say you want for pressure 0.3. So if 0.3 if in between, you either can do interpolation of the question or you can approximate based on the table. So it will be in between this and this. Okay, 0.28 and 0.32. It will be in between. Okay, the temperature is 30 degrees Celsius. So we know that 30 degrees Celsius is here. So we can take into consideration these two. So we know that for 0.32 is 0.0731 and for 2.8 0.83. So the value will be in between 0.07 0.07231 to 0.08338. So you can use the interpolation to find the value. So like in lecture note, they give here 0.07767. Okay, so the value will be in between. So if you cannot really find, you can just assume the value. So assume, so for P equals to 0.3 million Pascal, the value of V is 0.07767. Assume. And H2 is in between 276.65 to 277.41. In the lecture note is given. Okay, so here I think they refer to another table, so you get 274.7. It's okay, but it will be almost the same. Okay, okay, so this is how you read from the um, thermodynamic table. Okay, so I go back. Okay, so these are the information that we got earlier from the table A13. So V1 equals to 0.04064 and H1 equals to 338.19. Okay, sometimes the values might be a bit different because depends on the thermodynamic table that that particular company generate. So as long the values are almost the same nearby, so we still can accept. Okay, and for the second part, V2 equals to 0.07767 and H2 is 274.7. Okay, so you already got these two values, then you can replace it in this formula. Okay, the formula given here. So H2, okay, it's given here and 274.7 minus 338.19. So plus V2 you want to find minus 20. So 20 is given in the question. Okay, so velocity is with a velocity 20 degrees Celsius. So V1 is given over 2. Okay, so you solve this unit conversion. So V2 you get 356.9 meter per second. Okay, so that's for the first part. So you already got the exit velocity. So now we want to find ratio of inlet to exit area. So A1 minus A2. Okay, so you take this formula. So since M1 equals to M2, so 1 over V2 A2 over A2 V2 equals to 1 over V1 A1 V1. Okay, so this is from the previous formulas. So you rearrange, you get A1 over A2 equals to V2 over V1 V1 V2. Okay, so the smaller V is the volume flow rate. Okay, and V1 equals to velocity. Okay, so don't get confused. Okay, so you replace the values. So you get the ratio normally won't have unit. Okay, so you from here you get the ratio is 9.34. Okay, 9.34. Okay, so that's for the nozzle. So now we go to the turbines. Okay, nozzle, the area will be like this. Okay, so opening area will be more, exit area will be less, and for turbine it will be this, like this. The entrance will be small and exit will be bigger. Okay, so turbine drives the electric generator in steam, gas, or hydroelectric power plant. So most of the power plant in Malaysia, we are using hydroelectric. We are using water power or the wind power or steam power. Uh, okay, so it can be like the water in the form of steam or gas, or you can use any gas, or you can use hydroelectric power plant. Okay, in order to generate electricity. So inside there we have turbine. So you always have a turbine. So the flow will rotate the turbine, and what will happen? The electricity is generated. Okay, as the fluid passes through the turbine, work is done against the blade. So normally inside here we'll have a blade. So when the flow is entering, it will rotate the turbine, and the work is done. Which are attached to the shaft. So it is more on the rotational work. Okay, as the result, the shaft rotates and the turbine produces work. So inside the turbine, when it rotates, if you move from one point to the second point, so meaning the work is done. So if we neglect the changes in kinetic and potential energy as fluid flows through the air diabatic turbine, okay, having one entrance and one exit, the conservation of mass and the steady flow first law become, so m in equals to m out, because it's one entrance and one exit. So m1 equals to m2 equals to m. So energy also become energy in equals to energy out, because only one entrance and one exit. So this is the formula as we see here. For turbine, we neglect the kinetic and potential energy. So kinetic energy here, potential energy here. So you neglect, and adiabatic. Adiabatic meaning no heat transfer. So Q net also becomes zero. Okay, and no workout. So no work in. So only got one workout going out, because the work is done on the turbine. Okay, so at the end, the formula will become, so m1 dot h1 equals to m2 dot h2 plus w out. Okay, so you rearrange this formula, w out become m dot h1 minus h2. Okay, these are the um, formulas that we can use, but here I don't give the example for the turbine, but is similar like nozzle. Okay, so end of chapter 8 part 1. So any question? Okay, ada soalan? Okay, so if no question, so as I say, we will have lab this week. I will update you back the time once I ask from the teaching engineer. Then try to finish up all the assessment that given. Okay, and for those who came late, so next week we will have quiz 2, similar like quiz 1. So we will have in the game format, and you need to answer a few questions. I will give a trial quiz 2 first, so that you won't miss out. Okay, so I think that's all from me. Okay, thank you.
Thank you, sir.